A cache seems simple. Read from the database once, put the result in memory, and future requests become much faster. But the moment you introduce a cache, you've created two copies of the same data, one in the database and one in the cache. The real challenge is keeping those copies consistent. Imagine a user's profile is stored in Redis and also in the database. A request updates the user's name in the database, but before the cache is updated, another request reads from Redis and receives the old value. The system is now serving stale data, even though the database is correct. One strategy is time to live, or TTL. Every cache entry expires after a fixed amount of time. This approach is simple because stale data eventually disappears on its own. The downside is that you must accept a window during which users may see outdated information. Another approach is explicit invalidation. Whenever the application updates the database, it immediately deletes or updates the corresponding cache entry. This provides fresher data, but now every write operation must remember to keep the cache and database synchronized. Things become even more complicated in distributed systems. You may have multiple application servers and multiple cache replicas. Invalidating one cache node doesn't automatically invalidate all the others. Systems often need pub/sub mechanisms or change data capture pipelines to propagate invalidations across the entire infrastructure. There are also subtle race conditions. Suppose request A reads old data from the database, while request B updates the database and invalidates the cache. If request A then writes its stale value back into the cache, you've just reintroduced outdated data even though the invalidation succeeded. This is why patterns like cache aside, write through, and write behind exist. Each one defines a different ordering of reads, writes, and invalidations in an attempt to balance performance with consistency guarantees. Cache invalidation is fundamentally a consistency problem disguised as a performance optimization. The hard part isn't making reads fast. The hard part is deciding exactly when cached data stops being true and ensuring every part of the system agrees on that answer.